In the vast darkness between galaxies, something stirred. It wasn't a star. It wasn't even a galaxy. It was a monster hiding in the light, silent, ancient, and hungry. Visual, swirling galaxies fade into view. Camera zooms toward a tiny point of light, barely visible near a fringe spiral galaxy. This isn't a sci-fi movie. What you're about to experience is real. A black hole unlike anything we've ever seen, silent, consuming, and mysterious beyond imagination. Welcome to the incredible story of HLX-1, a black hole so unique, so powerful, and so perfectly placed between cosmic extremes that it could solve one of the universe's loudest missing puzzles. It might just be the most convincing intermediate black hole ever discovered and yes, that's a very, very big deal. A title appears, HLX-1, the most convincing intermediate black hole ever found. But first, what even is a black hole? Let's rewind the cosmic clock for just a bit. A black hole isn't just an object like a planet or star. It's more like an event, a location in space where gravity goes absolutely insane. It's so strong, not even light can escape. Pretty spooky, right? We categorize black holes based on their mass. Small ones, born when massive stars die, are called stellar black holes. They're around 3 to 100 times the mass of our Sun. On the other end of the spectrum, we've got supermassive black holes, found at the centers of galaxies, and these beasts, they're millions to billions of times heavier than our Sun. Think, the kingpins of the cosmos. But between those two titans, we've always suspected there's a middleweight contender. Something called an intermediate mass black hole, the long-lost link between the small and the absurdly huge. Theoretically, they should exist. But every time astronomers thought they found one, alternative explanations would ruin the celebration. The evidence, too flimsy. The calculations, too uncertain. The cosmic proof, always slipping through our fingers, until something changed, spectacularly, in 2009. A flicker appeared from the sidelines of a distant galaxy, and it refused to be ignored. It started with a space telescope, XMM Newton to be exact, orbiting high above Earth, scanning the sky in search of high-energy X-ray sources. Pretty routine stuff, until it spotted something dropping an X-ray beacon. Outrageously bright, far more powerful than it should have been, not quite located at the heart of a galaxy, that's the strangest part, but orbiting awkwardly, like a wandering satellite off course. Scientists dug in. They analyzed the location. The coordinates pointed them toward a spiral galaxy named ESO 24349, about 290 million light-years from Earth. Sitting quietly in the Phoenix constellation, and just off the edge of that galaxy, there it was, HLX-1a, hyperluminous X-ray source unlike anything ever observed. To put this simply, X-ray sources in the universe don't shine this brightly unless something very big is pulling matter in with unbelievable force and converting it into stunning amounts of energy. HLX-1 didn't act like a black hole at the core of a galaxy. It didn't fit the typical mold of a stellar mass black hole. It wasn't behaving like anything we'd seen before. And yet, scientists noticed sobering similarities to known black holes, especially something utterly It was bright enough to suggest a mass between 10,000 and 100,000 times the mass of our Sun. Cue the goosebumps. This was textbook intermediate mass territory. And suddenly, what was once theoretical was real. A missing link in our cosmic zoo had just raised its head. And what's more, HLX-1 wasn't just sitting there. It was pulsing. Every few hundred days, HLX-1 would flare up with intense X-ray emissions, proof that it was actively feeding on something. These flares were regular, rhythmic, disturbing. So here's the chilling twist. That feeding likely comes from a star, a companion star, trapped in orbit around the black hole. And every time it gets too close, it loses material. Tides rip it apart, and a stream of its matter spirals into the black hole's accretion, disketing up to unthinkable temperatures and releasing an explosive flare of X-rays into the universe. It's the cosmic equivalent of a predator feasting in cycles, one horrifying bite at a time. But things get even stranger. HLX-1 isn't at the center of that spiral galaxy where we usually find black holes. It's just floating, like it doesn't belong there. Like it's been dropped off. One theory. HLX-1 might once have ruled over its own galaxy, a tiny dwarf galaxy, devoured long ago by the bigger spiral galaxy ESO 243-49, and all that remains today of that little galaxy, HLX-1, a survivor, a remnant, a lone black hole wandering in exile. If that's true, this isn't just an isolated event, it's galactic archaeology. We're peering into the ancient remains of a cosmic tragedy, seeing how galaxies collided, merged, and evolved. HLX-1 is more than a black hole. It's a story, billions of years in the making. And most of all, it's hard evidence. For the first time ever, an object that checks every box for the existence of an intermediate black hole was blinking right in front of our eyes. Astronomers didn't ignore it, because if HLX-1 is real, then it opens the floodgates. We now know that intermediate black holes can form, that they do exist, that they've been hiding in plain sight in galaxies. In star clusters, maybe even here in the Milky Way. HLX-1 changed how we look at the universe. It changed how we model galaxy growth. It gave scientists their first real proof of a long theorized family of black holes, and above all, it made us ask, how many more are still out there, maybe hiding in galactic outskirts, drifting between stars, silently feeding, waiting to be discovered. So stay with us, because the next chapter in this journey dives even deeper. We'll uncover what exactly makes intermediate black holes so unique, and why they remained in the shadows for so long. Like HLX-1 itself, their story is quiet but explosive. Hit that subscribe button, leave your space-loving questions in the comments, and prepare for part 2 of the story that might reshape everything we think we know about black holes. Until then, keep your eyes on those distant stars, because the universe, it's just getting started. There's a certain elegance in a mystery that takes decades to solve. For scientists, intermediate black holes were just that. A riddle buried between the biggest and smallest extremes of cosmic power. For most of astronomy's modern history, black holes came into well-recognized flavors. The first, stellar mass, black holes, leftovers from the deaths of massive stars. These are the cosmic vampires we've grown familiar with, feeding off companion stars, warping spacetime, even popping up in Hollywood movies. And we've found dozens of them, thanks to their dramatic behavior and the X-ray outbursts they trigger. The second type, far more extreme supermassive black holes, the ones anchoring entire galaxies. Every spiral arm, every cluster of stars, revolves around these gravitational titans. We know they exist. We've seen the signals. We've even captured an actual image of one. But the third kind, the one in between, that's where the mystery deepens. Intermediate mass, black holes, or IMB-Hs, were long considered theoretical. A middle class that didn't have proof of membership, too big to form from a single star collapse, too small to shape a galaxy. They were the unicorns of the black hole family, talked about, speculated on, but never confidently spotted. Why do they matter? Because if we can prove they exist, they answer one of the biggest puzzles in astrophysics. How do supermassive black holes get so massive so quickly? Think about it. A supermassive black hole can be billions of times the mass of the Sun, but early in the universe, just a few 100 million years after the Big Bang. Some were already enormous. That means either they formed under unknown conditions, or they grew much faster than we can currently explain. And here's where intermediate black holes change the game. They're the bridge. The cosmic stepping stones. Like growth spurts for black holes, as small ones merge and feed over time, they become intermediates, eventually evolving into giants. But if these middleweights are so critical, why are they so hard to find? The answer lies in one word: detection. Stellar black holes often have companion stars. They announce themselves through X-ray flares as they consume matter, Supermassive ones warp entire galaxies. We see them by observing how stars swirl around invisible centers. Intermediate ones, though, they're like ghosts. They usually don't have companions. They might not orbit other stars, and without gas to feed on, they go silent, completely undetectable to our traditional instruments. They're not loud, they're not flashy, but they exist. We're now sure of that, thanks to HLX-1. And here's the cosmic irony. The very blinking behavior of HLX-1, once every few hundred days, that rhythmic flash that let us find it, that's only visible because it's currently feeding. Asterisk, had that star not been there, orbiting just close enough to be grazed over and over, HLX-1 might have remained totally invisible. We would have missed it, like thousands of others. We suspect may be hiding in globular clusters, dwarf galaxies, or drifting between stars, silent, unfed, undetected. That's the terrifying beauty of IMBHs. They're probably everywhere, crouching between the cosmic shadows, waiting for something, anything, to fall into their gravitational grip so they can light up. Even just briefly, like HLX-1. Imagine that. Black holes thousands of times the mass of the Sun, hiding invisibly in the halo of our galaxy. And we wouldn't know they're there until the moment they strike. And that's exactly what makes HLX-1 so valuable. It's not just a detection. It's a proof of concept. The first real poster child of the intermediate black hole family. It checks the boxes, not too big, not too small, off-center from the galactic core, surrounded by just enough matter to give us a light show. And when you add up the numbers, the light curves, the X-ray intensity, and the mass estimates, it all lines up. This thing didn't get there by accident. It was forged by gravitational violence, maybe the core of a stripped dwarf galaxy, disrupted long ago, now orphaned, now feeding, now glowing. Astronomers couldn't believe it at first. Because finding one intermediate black hole gives us reason to believe more are waiting. In fact, some think they lie at the centers of globular clusters, those ancient spherical groups of stars that orbit galaxies like satellites. They contain some of the oldest stars in the universe, and possibly hiding inside a middleweight black hole anchor. Why haven't we confirmed them yet? Because unless something gets close, these black holes don't shine. And if there's no emission, there's no signal for us to track, so we sit and wait for nature to give us another lucky accident. Just like HLX-1. But astronomers aren't sitting idle. Advances in gravitational wave detection, thanks to observatories like LIGO and Virgo, have opened a new window. In 2019, scientists observed a merger, unlike any before, two black holes colliding, one of them seemingly an intermediate. Even gravitational waves, ripples, in the very fabric of space-time, are now helping to fill in the puzzle. The pieces are coming together. HLX-1. Unusual black hole mergers, stripped galaxies. X flares from satellite clusters. All of them pointing in the same direction. Intermediate black holes aren't just possible. They might be a fundamental part of how the universe builds. Structure. The missing link between dying stars and devouring megamonsters, if you think about it. That's the natural order of everything. Nature works in transitions. Middle steps. Gradual change. Intermediate black holes just mirror that logic. Tucked between the extremes in the same way, adolescence sits between childhood and adulthood, still dangerous, still growing, still misunderstood, but undeniably real, and now, thanks to HLX-1, undeniably here. Keep watching, because in the next part of our story, we're going to ask, how exactly did HLX-1 get discovered? Why was its location so strange? What instruments were used? And what secrets can be hidden in the faintest of cosmic signals, just beyond the edge of spiral galaxies, where X-rays blink softly in the dark? The real story of HLX-1's discovery is a tale of data combing, skeptical scientists, and one unexpected flare that rewrote the textbooks forever. You won't want to miss it, because the universe hides its biggest secrets in the smallest places, and we've only just begun to uncover its whispers. Started with a flicker. Just a tiny blip in a sea of countless Astronomical data, an insignificant pixel in the middle of a routine scan. The year was 2009. The telescope, XMM Newton, a European Space Agency observatory that has been silently scanning the X-ray universe since 1999. Its mission is to spot high-energy objects, things that can't be seen in regular light. Exploding stars, neutron stars, accreting black holes. The data team was going through a section of the sky near a well-known spiral galaxy called ESO 243-49, roughly 290 million light-years away in the constellation Phoenix. This was supposed to be an ordinary region. Nothing stood out about it until they noticed a brilliant X-ray source just outside the galaxy's core. Not inside the nucleus where you'd expect a supermassive black hole, but a bit off to the side. That alone made ears perked up when they ran the numbers on its brightness. They did a double take. This wasn't just any X-ray source. It was hyperluminous, blazing far beyond what any ordinary stellar black hole could explain. Immediately, questions flooded. Was it a fluke in data? Was it some instrumental glitch? Could it be a background quasar lined up by chance? Or was it something the astronomical world had been waiting for? For decades. They reran the data, triple-checked it, looked at observations from different archives. Nothing explained it until they started calculating mass estimates from the brightness. Sultan's argument, the Eddington limit, and blackbody radiation models all suggested one thing. Whatever this was, it had to be thousands of times the mass of our sun. Too heavy to be a stellar black hole. Too small and too misplaced to be a supermassive black hole, and too bright to be ignored. The most logical explanation left, an intermediate mass black hole. It was named HLX-1, standing for hyperluminous X-ray source 1. And to this day, it remains the brightest of its kind ever detected at that distance. But even then, scientists weren't convinced. Astronomy is a slow, careful science. Claims of a new class of black hole can't be made lightly. You need long-term behavior, patterns, spectra, movement. So teams across the world began pointing their X-ray telescopes, optical telescopes, even radio arrays toward HLX-1. And quickly, it became clear. This was no mistake. They observed regular flares, massive boosts in X-ray output every 370-ish days, suggesting a feeding cycle. It was acting like a textbook, accreting black hole, taking in matter and converting it into pure energy. But that location, it kept bugging them. Why was HLX-1 not at the center of ESO 243-49? Why was it floating so far out, about 3,000 light-years above the galactic plane? Most black holes with this kind of activity are snug in galactic centers or paired inside stellar systems. HLX-1 appeared completely stranded. The breakthrough came when scientists looked at the optical counterpart of faint light coming from the same region in visible wavelengths. They hypothesized that HLX-1 might be housed inside a faint, star cluster-like object, maybe the dusty, shredded piece of a dwarf galaxy that had been gobbled by the larger galaxy long ago. Picture it, a small galaxy, pulled in by ESO 243-49's gravitational hug. Stars ripped from it, gas stripped away, but left at its heart a solo black hole, still alive and still feeding from whatever was left around it. It even had a star one, last companion, maybe a rebel survivor of its original galaxy, orbiting HLX-1 in a tight, eccentric path. And every time it nudged too close, matter would be pulled off, sparking those X-ray bursts. The story wasn't just about discovery anymore. It was about cosmic survival, a black hole, born in one galaxy, left behind in another. Still blazing, still powerful, still capable of sending radiation across 290 million light-years to Earth, where a tiny telescope lens picked it up over coffee and data sheets. That's the beauty of HLX-1's discovery, because it was not sitting in plain sight. This wasn't luck, it was patience, precision, and persistence. In the years that followed, HLX-1 continued to light up like clockwork. Every flare refined our understanding of its mass, structure, and origin. And every flare made the evidence stronger that this wasn't a freak anomaly. This was probably what we'd been searching for all along, an intermediate black hole in the open, not hidden in theory, but real, measurable, active. More observatories joined in, Chandra Swift, Hubble, even ground-based optical telescopes tracked and studied HLX 1 year after year, and all data confirmed the same thing. This wasn't a background quasar or an unlucky star. This was a massive accreting object in orbit around a host galaxy shining in precise, predictable intervals. That's not just a curiosity. That's gold standard data in the world of astrophysics. And here's the part that truly excites scientists. It means HLX-1 may not be unique. It may just be the first that's close enough, active enough, and well-placed enough for us to observe, which implies there may be thousands more like HLX-1 out there. Intermediate black holes may be hiding in far more galaxies than we imagined. Our understanding of how galaxies evolve from small to medium, two spirals like our Milky Way might depend on the mass lives of black holes like HLX-1. All from a tiny flicker, barely seen, just off to the side of a quiet little galaxy, 290 million light-years away. In science, discovery often happens in the margins, in the edge of a scan, in the shadow of larger things. HLX-1 may have been buried on page 12 of a data dump when it first appeared, but now it's on the front page of black hole history. And in the next part, you'll hear how it continues to challenge theories, especially when compared to its much bigger cousins, those supermassive monsters in galactic cores. Because if intermediate black holes like HLX-1 really are this common ... then our entire understanding of black hole growth, galaxy mergers, and possibly the early universe itself is about to get rewritten. Imagine a star, just like our sun, burning bright, living its quiet life somewhere in a distant galaxy, completely unaware of what waits in its orbit. Then one day it drifts too close to a dark, invisible monster. It doesn't explode, it doesn't go supernova, it stretches like taffy being pulled apart in slow motion. Its core collapses, its outer layers are torn away, sucked into a swirling disk of death, and within hours, light brighter than millions of suns erupts not from the star itself, but from the violent hunger of a black hole. That's what HLX-1 is doing, not just once, not as a fluke, but in a rhythmic cycle, over and over again. And the victim, a companion star, caught in one of the most tragic, awe-inspiring orbits in the observable universe. Here's how it works. HLX-1 isn't just floating randomly in space, it's got company. There's a star, smaller one, likely just a fraction the mass of our sun, that's orbiting it in what we call an eccentric ellipse. That means it swoops in very close at one point in its orbit, then swings far out, and every time it hits that closest approach, the peristron, it crosses the black hole's Roche limit. That's the gravitational point of no return, where tidal forces become so immense, they strip material right off the surface of the star and drag it into the black hole's accretion disk. This doesn't happen gently. The matter that gets torn off accelerates toward HLX-1 at incredible speeds, forming a disk shape and heating up so ferociously that it radiates X-auras, the brightest kind of light in the energetic universe. To astronomers, this X-ray spike acts like a beacon. We've got ingestion in aisle 5, and we've seen it happen with clockwork precision approximately every 370 days. HLX-1 gets a fresh meal, not the whole star. Just a taste, enough to light up space across millions of light-years. This cycle of destruction is called episodic accretion, and it's one of HLX-1's most defining and horrifying features. Now, try to imagine that happening over and over. A star, coming close, losing mass, retreating, only to return again next year. Lighter, weaker, doomed, over time. That companion star will lose more and more of its structure, like a comet losing ice with each orbit around the Sun. In this case, the end is not evaporation, it's full-scale annihilation. Eventually, it will become too light to survive. One day, in some future orbit, HLX-1 will consume it completely. No more flares. No more cycles. Just silence. But for now, we still get a glimpse of this deadly dance. Now here's the wildest part. HLX-1's regular feeding pattern is one of the main reasons scientists are so confident it's an intermediate black hole. Why? Because the timing and the brightness of those X-ray outbursts match the theoretical predictions of how a black hole in the 10,000 to 100,000 solar mass range would behave if it were fed by a moderately sized star. Smaller, stellar black holes show faster cycles and shorter outbursts, supermassive ones. They work on timelines of millennia and don't flicker like this at all. BHLX-1. Just right, even its light curves, the way the brightness rises and falls match models that fit intermediate black hole behavior. The flare rises quickly, then decays over a few weeks, before returning to a quiet, low luminosity state. It's the perfect crime scene profile, and that star's pain is our treasure, because without it, HLX-1 would be invisible. Just another space phantom, drifting through ESO 24349. Unannounced, it's this act of consumption. This tiny tragedy playing out over centuries that gives us the clues we need to hunt down a whole new class of cosmic objects, and it raises new questions. How did that companion star survive in the orbit for this long? Was it originally part of HLX-1's host dwarf galaxy, or was it captured sometime after HLX-1 was flung into its current location? We don't have clear answers yet, and maybe we won't, at least not until more HLX-1-like systems are discovered and compared. But what we are seeing is a real-time process of growth. HLX-1 is actively gaining mass. In essence, we are watching the middleweight champion of the universe slowly bulk up over time. Here's another haunting thought. What happens when HLX-1 finally finishes that star? Will it go dormant, waiting for a new victim, or will it drift quietly into space, dark again, invisible for eons, until something else crosses its path? Whatever the answer, what we're witnessing right now is rare. We're watching an intermediate black hole grow, not theoretically, not on simulation, but in nature. In real time, light years away, like a live broadcast of the universe writing its own rules. Some scientists have even compared this process to black hole adolescence. HLX-1 isn't young, but it's not yet fully grown. It's in a cosmic in-between. And like teenagers going through growth spurts, it's hungry, desperately hungry. But this hunger is cold, merciless, predictable. And every year, the star makes its fatal encore, and the curtain rises on one more act of destruction. In the next chapter, you'll finally meet the setting of this cosmic horror story up close, the galaxy known as ESO 243-49. We'll explore how this peaceful spiral galaxy may be hiding a much more haunted past. And more importantly, why HLX-1 being found there tells us something very big about how galaxies form, collide, and evolve. Because this isn't just about one black hole, it's about many. And if galaxies, like ESO 243-49, are the stage, HLX-1 might just be the lead actor in a story the universe has been trying to tell us from the beginning. It looks ordinary at first glance. Just another distant spiral galaxy, quietly spinning in the cold depths of the constellation Phoenix, about 290 million light-years from Earth, slightly edgy on in our view. A faint, silvery swirl of stars with a yellowish bulge at the center and spiral arms stretched out like slow-moving currents of stardust. But looks can be deceiving, because the galaxy known as ES 243-49 might be holding on to a cosmic secret, a puzzle piece, a fingerprint from a crime that took place long, long ago, not a crime of blood or war but of galactic cannibalism. Here's what we know. ESO 243-49 is the galaxy associated with HLX-1, the strange, hyperluminous X-ray source scientists discovered in 2009. But unlike supermassive black holes, which sit right at the hearts of galaxies like watchful gods, HLX-1 is not in the center. It's offset above the galactic plane by about 3,000 light-years detached, isolated, it doesn't belong there. Think of a solar system with its sun orbiting Pluto, it just doesn't add up. For a while, that was the biggest mystery. HLX-1 didn't fit into the neat models. So scientists began digging into the past of ESO 243-49. And slowly, a new theory began to emerge, something beautiful and brutal. The clues pointed toward a collision, a merger, long ago. ESO 243-49 may have absorbed a smaller galaxy, a dwarf galaxy, the cosmic equivalent of a space minnow compared to the spiral shark that devoured it. When galaxies merge, things get messy. Stars are tossed around, orbits are disrupted, and black holes, yes, even black holes can be flung off center. But something often survives. The dense core of the smaller galaxy, and at its center, a black hole, which is exactly what HLX-1 might be, not a native dot, an immigrant, the exiled heart of a devoured world, now orbiting the outskirts of its conqueror. When astronomers zoomed in, they found more than just They spotted a faint star cluster around HLX-1, not a galaxy. But not just empty space either. A remnant. A trail of cosmic breadcrumbs, possibly the remains of stars that once belonged to that dwarf galaxy, still circling HLX-1, still hanging on. That discovery changed everything, because now, HLX-1 wasn't just an anomaly. It was a survivor. And its location made sense. When a small galaxy is consumed, its central black hole can continue orbiting inside the larger galaxy's halo for millions or even billions of years. Still active, still dangerous, almost like a stowaway trapped between stars. Even more stunning, some of the stars near HLX-1 showed unusual light signatures, the kind associated with young star formation, which could be the result of the recent merger. As if the collision didn't just destroy things, it may have created something new, a spark of life in the shadows of destruction. So let's put the pieces together. We have a spiral galaxy, ESO 243-49. We have a strange, ultra-bright X-ray source orbiting far off-center. We have a faint cluster of stars tied to that source, and we have flares of high-energy radiation every year, caused by a black hole feeding. What does it all mean? It means we're likely looking at a black hole that was born in one galaxy, flung into another, and is now actively growing. Let that sink. In HLX-1 may be living proof, not only of intermediate black holes but of how galaxies evolve, how they consume each other, and how black holes persist through it. All gravitational kings, refusing to fade, no matter the chaos. Now, here's where things really start to blow open. If HLX-1 is the product of a galactic merger, then it's not just a one-off. Because, in the grand history of the universe, mergers are everywhere. Our own Milky Way will eventually collide with the Andromeda Galaxy in a few billion years. Astronomers believe both galaxies have merged, with smaller ones many times before. That means ESO 243-49 isn't rare. It's typical, and that means HLX-1 may be just one example of many lurking MBHs that came from other galaxies. Wandering ghosts, homeless black holes from eaten dwarf galaxies, still circling the skeletons of their new homes, and if that's true, then almost every major galaxy today could contain a few of them not in the center, but on the fringes, quiet, hidden, waiting. That's a terrifying and thrilling idea. It explains the scattered, elusive nature of intermediate mass black holes. It's not that they're rare, it's that we've been looking in the wrong place. We've been staring into galactic cores like detectives, focusing on the obvious suspects, but HLX-1 is telling us, look outside the center. Look at the scars. That's where the forgotten monsters live. And ESO 243-49, it's the crime scene. A silent witness to a violent cosmic event from millions, maybe billions of years ago. A beautiful, spiral-shaped scar, hiding a monster that shouldn't exist, and yet, it does. In the next section, we'll look at what HLX-1 means for science itself. We'll unpack why this object didn't just surprise people, it challenged models across the board. Because from the moment this strange X-ray beacon lit up on astronomers' screens, it didn't just confirm the existence of an intermediate black hole. It challenged everything we thought we knew about how black holes form, grow, and behave in the universe. Let's start with the basics. Before HLX-1, we had a neat model of black hole classification. Small ones are born from star deaths. Big ones sit in galactic centers, formed from mergers and endless accretion over billions of years, and in between, a gap that scientists either shrugged off or filled with theories. Some said intermediate mass black holes might form in early dwarf galaxies. Others thought they might emerge during massive star cluster collapses. Some argued they'd form only under the extreme conditions of the early universe. But the problem? No one had ever really seen one with solid, convincing, long-lasting evidence. Sure, there were hints, unusually bright, X-ray flashes, odd gravitational lensing events, unconfirmed mass estimates with huge error margins, but nothing that stood up to serious scrutiny for long. Then came HLX-1. Bright, patterned, reliable, and measurable dot with mass estimates between 10,000 and 100,000 solar masses, consistent flaring behavior, and a trail of evidence pointing to a past galactic merger. It didn't just appear out of nowhere, it fit, perfectly, right, into that missing space. But here's why it really shook up the field. Until then, many astrophysicists believed that intermediate black holes couldn't survive long enough to be seen this clearly. They'd either grow rapidly into supermassive black holes or fail to accrete enough and stay silent forever. HLX-1 broke that assumption. It said, not only can IMB-Hs exist, they can survive galactic collisions, hold on to their mass, and actively feed across billions of years. And the repercussions of that are staggering, because HLX-1 implies that intermediate mass black holes can be created outside of extreme early universe conditions. They don't have to be embedded in huge star clusters or dense galactic cores. They can travel survivors orbiting through larger host galaxies. Think about that. If HLX-1 really is the remnant of a smaller, cannibalized galaxy, it tells us that not all black holes live in cosmic skyscrapers. Some are refugees torn from their homes, carrying their history in their orbit, continuing to shine in exile. Suddenly, the science community had to go back and rethink. Do globular clusters hide more IMB-Hs than we thought? Could off-nuclear X-ray sources in other galaxies be more than just random anomalies? How might early black hole formation models need to evolve now that we know this middle evolutionary stage actually occurs? And the questions didn't stop there. Because once you realize HLX-1 is real, you have to ask, how many HLX-1 South have we missed? What if they're common, not rare? What if IMB-Hs helped seed the very first supermassive black holes in the early universe? What if galaxies couldn't evolve without them? Those aren't small tweaks to our understanding. Those are tectonic shifts in astrophysics, and HLX-1 caused them. Not with a dramatic explosion or new law of physics, but by being there. Flashing once a year, feasting quietly, orbiting alone, a steady, stubborn contradiction to our most comfortable theories. But that's the nature of discovery, isn't it? The moment you think you understand the cosmos, the universe whispers, look again. That ripple effect of HLX-1 touched nearly every branch of cosmic science: galaxy evolution, accretion theory, star cluster dynamics, black hole feeding patterns, and gravitational wave model. In it even helped refine how we calibrate X-ray telescopes. Because it became a case study, a known variable in a field full of unknowns, observatories began prioritizing off-nuclear X-ray sources in galaxy surveys. Catalogs of ultraluminous X-ray sources called HLXs were examined. Suddenly, galaxies previously dismissed as quiet were seen with new eyes. Maybe they weren't so dull. Maybe they had HLX-1 south of their own, and we weren't listening before. HLX-1 also changed how we communicate science. For young researchers, it was a perfect reminder: never overlook the faint offbeat signals. Sometimes, the game changer isn't the bright center, But the flickering anomaly on the edge, it gave hope to astronomers sifting through seemingly boring data. It inspired new energy in tracking down elusive IMB etchers through gravitational wave analysis. As observatories like LIGO and Virgo became more sensitive, so no HLX1 isn't just a blip in a database, it's a torch, one that illuminated a whole pathway we'd been wandering in the dark. And while it doesn't give us all the answers, it points toward new methods of detection, new stories for how galaxies grow, new types of black hole families, each shaped by violence, migration, and time. And most of all, HLX1 proved one universal truth in science. Sometimes, the most powerful discoveries don't shout, they flicker, gently, rhythmically, like a cosmic heartbeat tapping on the glass of the observable universe. In the next part, we'll follow that flicker through time. Because HLX1 isn't just a rogue object, it's also a messenger, a relic of a forgotten galaxy, a leftover from an ancient era. And by studying it, we may uncover how supermassive black holes are born from seeds like this one. Get ready, because we're about to journey deeper into the cosmic past to find out what HLX1 is really telling us about the origin of galaxies themselves. Every black hole tells a story. But HLX1, it's not just telling us about itself, it's whispering secrets about the infancy of galaxies, and maybe even the early days of the universe itself. To understand why that matters, we need to go back not just millions, but billions of years. Back to the time when the first galaxies were forming. The early universe was chaotic then, full of clouds of hydrogen, forming stars, and collapsing structures. Gravity was writing its first stories, but the punctuation marks were missing. Because somehow, by the time the universe was just 700 million years old, we already see supermassive black holes in galaxies. Black holes the size of billions of suns, fully developed, settled into galactic centers. Pause for a moment. That's like finding a full-grown tree in a forest that just sprouted yesterday. How did those monsters grow so fast? That's the great mystery. One of the biggest in astrophysics today. Scientists have long assumed there had to be a seed-stage black hole that wasn't formed in a galaxy center, but inside smaller structures, a middle step that could serve as a foundation. This is where HLX1 speaks volumes, because it's exactly what those early seeds might have looked like: a black hole formed in a small, possibly dense dwarf galaxy, slowly consuming matter, gaining mass, and eventually merging into a larger galactic structure. That's the blueprint, and HLX1 is the first observational proof that this kind of object doesn't just happen once. It happens routinely. Think of it this way: H1 was likely the central black hole of a dwarf galaxy. That dwarf galaxy collided with a larger one. ESO 243 - 49 its home was stripped away. Its stars scattered, but the black hole survived. In orbit, feeding. Visible now, draw that backward. In the early universe, thousands of smaller protogalaxies likely collided. Over and over, each one could have had its own HLX1-like black hole. And each time, they combined, those black holes may have merged, or settled, near the center, building up the colossal entities we now call supermassive black holes. Suddenly, the impossible becomes inevitable. Black holes didn't appear out of nowhere. They grew from ancient ancestors intermediates, like HLX1, forged in chaotic environments and assembled like bricks of gravity. And this brings us to a fundamental shift in understanding. Black holes don't just end lives. They create structure. They anchor galaxies. They help regulate star formation. They even shape how galaxies spin and collide. So when we find one like HLX1, we're not just seeing a black hole, we're looking at a potential origin point of galactic architecture. Here's where it gets even more fascinating. Recent simulations suggest that black holes of HLX1's mass around 10,000 to 100,000 solar mass form not just in dwarf galaxies, but in massive star clusters during the early universe. In dense, chaotic regions filled with young stars, gravitational interactions can cause core collapses. funneling matter so efficiently that an MBH forms in the center. These become anchors, gravitational centers. Eventually, galactic cores. HLX-1 may be the descendant of one of those early clusters, a kind of time capsule, accidentally preserved in the modern universe. A message in a bottle from 13 billion years ago. And guess what? If HLX-1 made it this far through the merger, through ejection from its original nucleus, through the gravitational chaos of a galactic collision, then others have too. There could be dozens, maybe hundreds of HLX-1-like objects floating around in nearby galaxies. Not central, not supermassive, but ancient, foundational, necessary. That's why astronomers everywhere are paying attention, because HLX-1 shows we need to rethink galaxy formation, not as a top-down process, but bottom. Not as enormous black holes forming at once, but as accumulations of stars, gas, and yes, smaller black holes, each one merging, colliding. HLX-1 fits into a new cosmological puzzle we're only beginning to unlock, and we now have better tools than ever before to carry on the hunt. The James Webb Space Telescope is searching deeper into the early universe, identifying faint galaxies and quasar candidates from the first billion years. LISA, the Laser Interferometer Space Antenna, launching in the 2030s, will search for gravitational waves produced by IMBH mergers, giving us brand new ways to spot the seeds and archives of galactic data once brushed ASIDAR being reanalyzed with AI-driven algorithms that can detect subtle light curves and off-center X resources, all thanks to the example HLX-1 set, one black hole, one galaxy merger, and a ripple through our entire understanding of cosmic growth. So if you've ever looked up at the stars and wondered where it all began, know this: the answer might not come from the brightest part of a galaxy or the loudest cosmic event. It might come from a ghost, flickering softly at the edge of a galaxy, carrying with it the memory of a time when galaxies were still forming, and black holes were just learning how to become gods. In the next part, we're going to pull back and compare HLX-1 to its cousins, the familiar types of black holes you've probably heard about, because if HLX-1 is the missing link, then understanding how it stacks up against stellar black holes and supermassive ones could be the key to finishing the cosmic family tree. Stay with us. The universe is about to introduce all of its children. When people think of black holes, they usually imagine two things: something stellar-sized, maybe a few times bigger than our sun formed after a supernova, or something absolutely even billions of times heavier than our sun looming at the center of galaxies like cosmic monarchs. But HLX-1, it doesn't fit either mold. It lives in the space between, the forgotten middle child of the black hole family, and the more we look at it, the more it becomes clear this middle child might actually hold the entire family together. Break down the black hole hierarchy for a moment, because understanding the differences is key to just how unique HLX-1 really is. At the bottom of the black hole ladder, we have the stellar mass black holes. Born from the collapse of massive stars, these black holes are fairly common across the galaxy. They typically range in mass from 3 to maybe 100 times the mass of the Sun. Though most hover closer to 5 or 10. They often live in binary systems, orbiting with a companion star, feeding on it over time, and flaring up in X-rays when that matter falls inward. We've found dozens of these already. NASA's Chandra X-ray Observatory, XM Newton, and now even gravitational wave detectors help us catch them in the act. Now, jump with me all the way up the ladder to the top. The giants. Super black holes. These monsters are millions to billions of times the mass of our sun. We've confirmed them at the center of every large galaxy ever studied, including our Milky Way. Sagittarius A*, the one at our center, weighs in at about 4 million solar masses. Some quasar cores in the early universe host black holes nearing 10 billion solar masses. They're ancient, powerful, and likely formed through countless mergers and accretion events over cosmic time. But here's the catch: there's a huge, awkward gap between the biggest of the stellar mass black holes and the smallest of the supermassives, that mysterious middle zone from about a few hundred to a few 100,000 solar masses, was empty. Mathematically possible, theoretically predicted, but observationally missing. That's where HLX-1 breaks the silence. Its estimated mass, somewhere around 20,000 solar masses, too big to be stellar, too small to be supermassive, but just right to open a new chapter in the black hole family tree. Now let's compare. Feeding behavior. Stellar mass black holes feed with short chaotic outbursts. Their flares can last hours to days. Supermassive black holes operate on slow, centuries-long cycles. Their meals are enormous, but drawn-out gargantuan swallows of gas and dust over eons. HLX-1 flares once every year, fast enough for human observation, long enough to reflect a much more powerful gravitational field. The duration and shape of its light curves match what we'd expect from an intermediate black hole. Its behavior isn't random, it's rhythmic. Predictable. That single quote's almost unheard of in this part of the mass spectrum. Location. Stellar black holes are scattered all over galaxies and arms, borders, and even interstellar space. They're lonely, or in binaries, but they're not in charge. Supermassive black holes are always in power, literally central, folded deep into the cores of galaxies, shaping star formation, gas dynamics, and galaxy morphology itself. But HLX-1, on the edge, orbiting quietly, its position thousands of light-years away from the galactic nucleus, immediately sets it apart as something different, something that doesn't belong in the models built for supermassive or stellar black holes. And here's the most fascinating part. HLX-1 may be a stepping stone, a black hole in transformation. Some scientists believe intermediate black holes evolve through a series of mergers. Tiny black holes pull in stars and gas, then merge with other black holes, creating larger cores. Over time, multiple intermediate black holes can collide, especially during the merger of small galaxies, and eventually form a supermassive core, which means HLX-1 may not just be different, it may be a missing chapter in the origin story of supermassive black holes. We may be watching it grow in real time. And the best analogy: think of black holes like animals. Stellar black holes are like wolves, small and fast and often working in pairs. Supermassive black holes are elephants, slow-moving, immovable, and ruling their environments. But intermediate black holes, they're somewhere in between. Predators no one's ever fully seen in the wild. Until now, HLX-1 is our first good sighting. So, how do we know HLX-1 isn't just a scaled-up stellar black hole or a scaled-down supermassive one? Because its luminosity, feeding patterns, and mass estimates put it squarely in no man's land, and more importantly, it's consistent. Not a one-time flare. Not a false positive. Year after year, flare after flare, HLX-1 continues to behave exactly like an intermediate mass black hole should. That alone makes it a standout in black hole catalogs around the world. It's like finding the missing bridge between ancient stone tools and modern machineries. The jump from simple to complex doesn't seem so mysterious anymore. HLX-1 fills that evolutionary void. It connects the dots, and if there are more like it out there, we might soon have a complete black hole family tree from newborn stellar remnants, 2 teenage intermediates, 2 ancient galactic emperors. In the next section, we'll look forward. HLX-1 gave us a path, but how do we follow it? Where do space scientists go from here? And how do you fit into humanity's mission to find the next HLX-1? Because the story isn't over yet, it's just getting started. Discovery is a door, but the real question is, what lies on the other side? HLX-1 didn't just give us proof of intermediate black holes. It handed us a roadmap, a trail of cosmic breadcrumbs pointing toward what's next, not just for astronomers, but for the future of black hole hunting itself. Because once you've found one, it means there are more out there. The question isn't if, it's where and how do we find them. Let's start simple. HLX-1 was only found because it was active. Bright, feeding, screaming its presence into the void with powerful X-ray blasts every year. But what about the others? What about the quiet ones? Because most intermediate black holes won't be surrounded by stars. Many will have already consumed or ejected their companions. They'll just sit, silent, dark, invisible, waiting for something to fall in. We're living in a universe where the majority of IMBHs might not be broadcasting any signal at all. So how do you spot something that refuses to shine? We evolve, and we already are. The next wave of black hole hunting is here. And here's what it looks like. First, X-ray surveys are getting deeper and smarter. Satellites like EROSITA and observatories like Chandra are being paired with machine learning models trained not just to look for obvious signals, but to predict where quiet IMBHs might be hiding based on indirect evidence. We'll hunt them the way fossils are sometimes found, not from bones, but from the shadows they leave in rock. Unusual star motion, odd gravitational anomalies, faint thermal signatures. These aren't dead ends anymore, they're red flags, subtle, insistent whispers that something's there. Then there's the optical side. Instruments like the Vera C. Rubin Observatory will scan the entire night sky every few nights, catching changes in brightness, motion, or shape that could point to black holes interacting with their environments. And, of course, there's the soundless symphony of space, gravitational waves. When black holes collide, they don't emit light, they ripple the very fabric of spacity. ACETIME.HLX-1 may not be merging right now, but others are. And with the upgraded LIGO, Virgo, and the upcoming space-based detector LISA, we're preparing to hear those ripples from intermediate mass black holes merging across the universe. A single collision could announce the existence of an IMB, even if it's 10 billion light-years away. That's not science fiction anymore. That's the next decade. And in case you're wondering, yes, HLX-1 may one day merge to, if it finds another black hole in its galactic wanderings, or if it drifts back into the nucleus of its host galaxy and collides with the central supermassive black hole. The resulting merger will create a flash, not of light, but of gravitational resonance, the ultimate harmony, the death of one black hole age, the birth of another. There's something poetically terrifying about that, but let's zoom in, because this isn't just about the future of science, it's also about the future of you, black hole. Discoveries no longer belong to just space agencies or billion-dollar labs. You, sitting at home, watching the stars through a telescope or a live stream, you are part of this next era. Public data repositories, from missions like TESS Transiting Exoplanet Survey, Satellite and Zwicky Transient Facility Z, open, accessible, waiting. Citizen science platforms like Zooniverse let users help classify galaxies, track brightness changes, and even flag strange events that AI might miss. And guess what? Some of the most unexpected discoveries in recent years have come from nan-scientists. From data nerds, from stargazers, from people just curious enough to dig a little deeper into the unknown. HLX-1 may have been found by professionals, but the next one, it might be tagged in a comment. Or caught in a shared image, or noticed during an all-night scroll through raw survey data at 2 a.m. This is the era of distributed discovery, where anyone with determination and access can help unlock the secrets of the universe. And the stakes are huge. Because finding more HLX-1 South could help answer some of the most profound questions we know to ask. How do galaxies evolve over billions of years? What are the real origins of supermassive black holes? Could solitary hidden black holes become threats to stars or even planets if they drift into the wrong part of space? There's even an idea, admittedly speculative, but haunting nonetheless, that rogue IMBHs could be passing through galaxy halos, completely undetected. Black holes without light, traveling at hundreds of kilometers per second, massive and invisible. If we can find them, we can understand them. If we can understand them, we can map them. And maybe one day we can learn just how common these middleweight monsters really are. HLX-1 was the beginning, a flare in the dark. But you're living in the era that comes afterward, and whether you're watching through a screen, editing these words into a YouTube upload, or staring up at the stars from your backyard with a telescope and a dream, you're already part of the search. In the final chapter of this journey, we'll look at the bigger picture. Everything HLX-1 has taught us, everything it represents, and the quiet, sobering truth that we're just beginning to understand the deep structure of our universe, one invisible giant at a time. The universe doesn't shout, it whispers, and every so often, that whisper travels across millions of light years, reaches the lens of a telescope, slips onto a datasheet, and changes everything. That's what HLX-1 did. It didn't explode, it didn't collide, it didn't bend time in some dramatic Hollywood twist. It just flickered once. Then again, and again, a soft but persistent pulse in the dark, reminding us, I'm here. I've always been here. And in that whisper, we heard the voice of something long believed, but never quite proven in immediate mass. Black holes exist not just in theory, not just in models, but out there, real, measurable, alive. HLX-1 shined and forced us to rethink everything we thought we knew about black holes and, more than that, about ourselves, our models, our assumptions, our blind spots. Because while science is built on data and equations, it's also anchored in belief, the belief that we're capable of seeing the universe for what it is, not just what we expect it to be. HLX-1 challenged that belief and made it stronger, because it proved that truth can hide in the background of low contrast on the edge of detection and still carry cosmic weight. In just one discovery, we connected so many dots: how black holes grow, how galaxies merge, how smaller structures feed larger ones, how chaotic beginnings build orderly systems, and how the darkest things in the universe still shape everything we can. HLX-1 also taught us patience, because it didn't flash once and disappear, it came back. Again and again, like a beating heart, and that rhythm gave scientists time to measure, to ask questions, to model, to believe. Confidence in science isn't built on spectacle, it's built on consistency, repeatable, reliable signs from the unknown. And HLX-1 showed up when we needed consistency most. In an era of new instruments, deeper sky surveys, and better cooperation across international observatories, it was the perfect mystery at the perfect time. But it also leaves us with the one question that every great discovery eventually does: where do we go from here? We push forward, eyes wide open, sensors ready. We search beyond the galactic cores, into Halo's outskirts, star clusters. We comb through gravitational wave archives and light curves from satellites orbiting Earth. We build better telescopes. Launch new missions. Train AI to see what human eyes can't. Because if HLX-1 has taught us anything, it's this: black holes don't need to be enormous to be important. They don't need to sit at the center to tell the central story, and they don't need to shout to be heard. Sometimes, an entire chapter in the story of the universe is written in a whisper. A barely there dot in the sky, a silent feeder in a galactic halo, a flare once a year, 290 million light-years away. And if that doesn't humble you, if that doesn't make you feel incredibly small, and yet incredibly connected to something far bigger than we can imagine, then maybe nothing will. So, we closer to unlocking the secrets of the universe. Yes, because we listened, and somewhere, out there in the dark, another HLX-1 is waiting to flicker. Waiting to teach us something profound, and when it does, we'll be watching, we'll be listening, and we'll be ready to understand the universe just a little bit more. So, thank you for taking this journey with us from the edge of a distant galaxy, into the heart of black hole evolution, and out the other side with new curiosity. If this episode sparked your imaginations, subscribe, like, and share it with someone who also looks up and wonders what's out there. Because stories like HLX-1, they're far from over, they're just beginning.